called Sher. I'm the infra software team lead at Datagen. And I have experience with over a decade of data engineering and software engineering. And today I'm going to speak to you about generating synthetic data at scale with the help of modern execution technologies with some emphasis on the infrastructure part. So just before we'll kind of go over the agenda, I would like to get more familiar with who am I talking to. So if you're a data engineer, software engineer, can you please raise your hand? Okay. I guess lots of NLP guys here, right? Or computer vision? Less. Okay. So I guess I can tell lies and that will go. So we'll talk today about the first thing we'll talk today, what is synthetic data in the scope of computer vision. After that, we'll tell you a bit of the journey of Datagen infrastructure. And then we'll kind of drill down into the challenges we faced during the creation of our infrastructure. So AI performance, as kind of said before, is kind of comprised of two main factors. The first of them is the model and its quality, and the other one is the data, and the data that was kind of the model was trained with. And there's a lot of ongoing efforts regarding making the models much better, much faster, much bigger, and more generalized. But kind of the data part, which have lots of potential, is not like being used to its fullest. So, and manual, also like said before, manual annotation, manual gathering of data is kind of have a lot of challenges with it, and it needs a lot of human intervention, which means it will usually take a lot of time and a lot of money. And other than that, it's kind of prone to a lot of human errors, data privacy issues, and biases, of course. So we at Datagen, our mission is kind of to teach the AI to see the world better with the use of synthetic or simulated data. So I guess there are not a lot of computer vision guys here, but I think that if there were, they probably think of synthetic data. They'll probably go for GANs, generative adversarial networks, and we're not be talking about that today. We're talking about something a bit different, more controlled. So in order to get this data, this simulated data, you first need to kind of capture real-world 3D-based content by scans, 3D scans, or by mock-ups, or any 3D content based on the reality. And then you can create a variety of 3D environments in a controllable way, which is very variant. And then you need to kind of extract the data out of it with some annotations at a high fidelity rendering. So in this example, you can see one 3D environment, which in every kind of object inside of it is some other separate 3D content, the human being, the trash bin, or the tables, and even the spoon, if there is one there. Even the tiniest piece here is kind of its own object. And you can see how we can take all of these kind of building blocks of 3D components and create a unique and variety of different environments in a programmatical and algorithmic way. So after we have all of this variety of different environments, we can then kind of extract the data out of it. Think about putting some camera inside of the 3D environment from one point of view, and then render it. It will usually use lots of GPUs just in order to do that quickly. And on the top left part, you can see some image that is kind of the reality image. And this specific image is it's an image that is a near infrared in this specific use case. And all the rest are kind of the ground truth and modalities of the same image taken from the same point of time, from the same exact moment and place. On the right bottom part, you can see the segmentation, where each kind of unique part of the 3D scene is kind of colored with a different color. And the other ones are talking about depth map and normals map. So you can probably guess how tedious work it will be if you try to manually annotate such data, and we can get them in a pixel perfect way. And other than that, we can also generate some textual data, textual metadata about the 3D environments, such as the bounding cuboids of each and every object inside of the scene, some key points like you see on the female's face and on the driver's body. So now that we've kind of understand better what it means, simulated or synthetic data in the field of computer vision, I'd like to briefly kind of take you into the journey of Datagen, specifically the infrastructure journey. So kind of 2 years ago, we were getting kind of ad hoc projects from customers specifying what kind of environments and how do they want their data to look like. And we kind of created some scripts to accommodate these variations of environments. And then we had like something like 4 PC computers like you see here, which we called monsters because they had lots of GPUs, CPU, and RAM. And we kind of logged into each and every one of them manually, ran the scripts, and then probably a day later, or maybe even more, it depends, came into the office, kind of manually collected the entire data set, put it on some hard drive, sent it away to the customer. And of course, this kind of was the naive approach 2 years ago. And of course, it's prone to a lot of problems, such as the cleaner lady that comes and pulls out the plug just because you want to clean beneath, and she did it actually twice. Yeah. And so a few months later, we kind of did things better, at least a bit better. And we've kind of put all of these monsters into somewhere centralized, in some rack. Started to use Celery. For the ones who were not familiar with Celery, Celery is some framework, Python framework for distributed processing. So now we were able to kind of start kicking off the generation from one central place, making sure that the entire computers, each of them will get their own part of the generation. But it still wasn't good enough, of course, because we still wasted lots of resources and there was no kind of central management of the entire workflow. So a few months later, we kind of started to create our own workflow management system. We called it Agni. It's some kind of an Indian god that was responsible for passing messages between the other gods or something like that. Shai is the one that's responsible for that name. And so now we kind of did things better. We split the tasks into a more granular task, which each of them had different resource consumption. Specifically, the tasks that needed the GPU rendering were kind of by themselves, And we have another central entity that was kind of orchestrating the entire workflow. But of course, it still wasn't good because we still had those exact same 10 GPUs we had before, and customers' requirements and orders kept coming in, and we and we didn't made it on time. So we knew we need to prepare to go into the cloud, where we'll probably have much more resources than we can have at the office. So the first thing we did is kind of replaced Celery with Kubernetes. So instead of sending tasks as Celery tasks, we've kind of sent pods directly into the Kubernetes cluster, still on-prem, but that what enabled us after approximately at the beginning of this year to deploy the entire infrastructure into AWS, and then not only leveraging just Kubernetes, but also Kubernetes cluster autoscaler, which was responsible to spin up instances up when we need them and down when we kind of ended with the generation. And approximately at the middle of this year, we kind of put all the pieces together and went GA with our self-service platform. And if I'll zoom a bit into this specific page from our face generator, you'll see that our users, our customers can specify whatever distribution of age, gender, ethnicity, eye color, look at directions of the eye, expressions, and so on. And then when they kind of click on the generate button at the bottom, kind of the whole magic at the back end starts to work. And the customer gets some kind of a link to download the data, which is much better than getting some hard drive, right? So that was in a brief. And now we'll kind of talk about the challenges we've faced when we kind of created this whole architecture. So we had to keep in mind we want to make things much as fast as we can, because the alternative is manual data collection and annotation. We want to be, of course, much better. And we need to be fault tolerant, because now we're going to be some SaaS service. We can't have no one manually being there to fix stuff. And GPUs are expensive, and we want to cut the cost, not only for us, also for the customers in the end. And we have lots of customers that may be generating data at the same time, and we want all of them kind of to have the same consistent service, no matter how many customers are generating at the same time. And the last one is kind of our developers we want our developers to be able to test their own changes of the workflow without having to kind of bootstrap this entire ecosystem. So if we drill down, specifically the first one will be regarding the generation time. So the first thing we did, we kind of splitted the entire generation into lots of tinier independent tasks. So in the first task would be some kind of a random generation of a 3D environment till the extraction of the realistic image and the ground truth. And each and every one would be something like that. And the thing is that if we have if we have n environment generations we need to do, and we have enough resources or n resources to accommodate all of these generations at the same time, we could potentially finish the entire generation at the same time of only one generation, right? So, but now that we've kind of spread the task into lots of distributed workers, things won't necessarily go as you want, and things might crash. So this was the kind of the point where we started creating Agni, a workflow orchestrator. And now we have, for each workflow, we have one instance that was responsible for the entire run of the workflow. And it was kind of listening to changes coming out from these workers. And whenever it identified that some of the tasks gone missing or might fail, it kind of was responsible to retry it, make sure it runs, and of course the entire generation completed successfully at the end. But when you retry a task, you need to make sure your tasks are idempotent. So for the ones that are not familiar with this term, so idempotency, or an idempotent task, means no matter how many times I'll run the same task over and over, its output will always be exactly the same. So for example, if this environment generation task started running, then failed, then the orchestrator found out and restarted it, and if before it kind of already wrote some files, and now it instead of overriding them, it writes another files, maybe with the .copy extension or something like that. Now the output is something else, right? And the overall result of the workflow could be very different. So the responsibility of writing these tasks and making sure they are idempotent is something each developer in Datagen, when it writes the task logics, it keeps that in mind and making sure the tasks are idempotent. So we already kind of talked a bit about GPU that is very expensive, and we want to make sure we are only using the GPUs or the GPU nodes only when we really need them. And so what we did next is we even splitted the tasks more. So now we have, for each environment generation, we have one task that is responsible only for the 3D environment generation, which usually uses only CPU. And then after that, it have two dependent tasks that one of them is using the GPU to render the realistic image, usually using ray tracing and things like that. And the other task is doing some CPU rendering and extraction of modalities, of textual modalities and things like that. So in this specific example, you can see that the first two environments were inside of the process of generating the 3D environment, while the last environment was kind of done with the 3D environment generation. And so the next few tasks kicked in. The first one went to the CPU nodes, and only the one that really requires the GPU went to the GPU nodes. But it's still not good enough. That maybe was good when we were working on-prem or on our own fixed machines, fixed number of machines. Sorry. But in the cloud, we want to make sure we don't have instances up and running if we're not really using them. So now that we've kind of deployed our infrastructure into AWS using Kubernetes, we were able to leverage Kubernetes Autoscaler, which was the one that enabled it was the one that was responsible to making sure that the number of instances or the number of hardware we have up and running at each moment is specifically the one we need in order to accommodate the tasks that we already sent for execution. And we already talked about being resilient and fault tolerant and having the ability to quickly recover from failures. So why not leverage spot instances? So for the ones who doesn't know, spot instances are a special type of instances the cloud providers can give you in a really good price. Usually, I think something like 1/10 of the price of if you compare it to the same type of on-demand instances. But they don't assure you that these instances will be up and running for the entire time you want them to be. So instances might get down and taken away from you, but that's usually fine because we are able to recover, and each of these tasks are usually quite small in runtime. So in the worst case, we'll probably go back only a few minutes backwards. And of course, we have multiple customers that might generate data on the same infrastructure on the same day and time, and we want to make sure each of them get the same exact service. So what we did, we kind of added some new feature into Agni, our workflow manager, that's now is able to, for each workflow, is able to get some resource capping information, which tells the workflow that how many resources it can use in each point of time. So in this specific example, you can see two customers' workflow. Each of them is capped with only 2 CPU tasks he can like send for execution at one time, and 1 GPU task he can set on one time. But of course, these are small numbers. In reality, we're talking about much larger numbers. We're talking about like overall, we're talking about thousands of instances altogether. And we said before that we want to make sure the developer have a nice experience with Agni and with creating workflows. And like testing distributed application is something that is usually very hard. You'll need lots of shared components, such as data stores or a shared file system. In this example, even Kubernetes. So what we did is we kind of created a decoupling between the workflow orchestration and the creation of the workflow and the part of the task execution themselves. So in production, we could have kind of plug and play for the same workflow. We could have kind of plug and play the Kubernetes executor, making sure all of the tasks are being sent to Kubernetes. And for testing, we could have used the same workflow, plug and play the local executor, and make and then the task will be executed on some local process pool. So, of course, we've kind of made a lot of progress, and we still have lots of ongoing challenges, such as making the scheduling much smarter in the field of estimation of time and resources, monitoring and visibility, dynamically changing the workflows, capping, helping the developer even test their changes in a kind of in a more production grade environment, and a lot more. And just to kind of wrap it up, we're now able to utilize thousands of instances in the cloud to support our many customers to generate data at parallel. We're talking about thousands of data points in only a few hours, and kind of help our customer train better AI model, just like we've kind of promised at the beginning, right? So usually you'll see these kind of slides, I think, in the beginning. Thought to put it here. But this is us, this is Datagen. Our customers are tech giants from Fortune 500 companies, from many verticals, and we are also hiring. So if any of this kind of sounds interesting, please do contact me or get into our website or whatever. So thank you. And